Hello, I'm Derek Hitchens, and I'd like to talk to you about systems design. Systems design may be seen as the keystone of systems engineering. So what is systems design? Well, it's not systems thinking, although that has a role to play. And it's not systems architecting either. And it's certainly not engineering design. No, it's the operational concepts, strategies, mission objectives, synthesis, aggregation, integration, organization, architecture, and presentation of a complete viable set of integrated dynamic functional systems, which, when realized in their operational environment, will optimally and sustainably solve the problem that prompted their creation. Phew, and that is a mouthful. However, we'll look at it a bit more simply. So what is system design? Let's start again. It provides a complete set of requirements for a comprehensive, sustainable operational solution system. Well, that's good. It not only identifies what has to be synthesized, but how that whole will operate, cooperate, strategize, sustain, adapt, evolve, self-heal and survive, etc. So system design defines solution systems of all kinds: technological, human activity, operational, social, societal, political, economic, educational, medical, even global. So what is system design again? So the plan, it's a straightforward plan, is to work out the emergent properties, capabilities and behaviours required of the whole solution system needed to solve the customer's problem. And that customer's problem is the key. And then to synthesize that whole solution system from interacting functions organised into a unified whole. The diagram at the right shows how one might go about solving complex problems. It's the systems engineering problem-solving paradigm. In systems design, parts identified by analysis of the functions to be formed by the whole are not put together like unchangeable pieces of a jigsaw puzzle. They are designed to fit each other so as to work harmoniously as well as efficiently and effectively. So said Russell Ackoff back in 1981. Pragmatically, the objective is to design a system that is going to perform and continue to perform in its operational environment, which will be continually changing and which may present risks, threats, attacks, damage, and of course, opportunities. If a system is to be viable, then it has some aspects to it. A viable system is one that can survive to function, perform and even thrive in its natural but inevitably changing environment. System design emphasizes total system environment interaction, whence we have the acronym SMESH. Survive external threats. And you can look at survive and say that it's got a number of aspects to it, like, for example, avoid detection, self-defense, damage tolerance, self-healing, and so on. Maintain, that's maintain internal functions and interrelationships. Evolve, that's adapt, renew and improve. That's really as the environment changes. Synergize, that's cooperate, coordinate and control. And homeostasis, or dynamic equilibrium, keeping the whole system on an even keel, as it were. Synergy and emergence. Synergy is the coordination and cooperation between, often between, two or more functions to produce a combined effect greater than the sum of their separate effects. So it's the emergent properties, capabilities and behaviours of the whole. Mission management is the coordination of and cooperation between the many mission functions to prosecute the mission. Similarly, viability management, behaviour management and resource management. And all four managements together give rise to the emergent properties, capabilities and behaviours of the whole when interacting with other systems in their operational environment. Here's a viable system model at the left. The viable body at the bottom provides a functioning baseline system on structured foundations and manages low-level behaviour and coordination. Intellect, the mission management, behaviour management, adds reasoning, understanding, purpose and mission. The operations function sense, then process, coordinate effectors and give reflex behaviour. And last but far from least is this overview of function management. Mission management, part of function management, is in red at the top. And you can see that mission management collects information from the operational environment, sets objectives, formulates strategy and plans. I'm following the red arrows. Executes the strategy and according to the plans and cooperates with others in the environment. That process has threats from in the environment and there may be changes going on. Down at the bottom we can see in blue the resource management model, and all you can do with resources really is acquire them, store them, distribute them, convert them to use and dispose of the waste. In the middle you can see the viability model, which is keeping everything stable as a platform for the mission management and resource management to work on. Mission and resource management together manage the flow or flux of information, energy and substance through the open system. System dynamics, I've got the system of interest there shown as the various managements and form, and the system of interest is sustained by two loops. There's a reactive loop where it produces an effect or a product or an outflow, and there's a reaction or a service inflow. And the other one is the resource environment, where there's a demand by the system of interest for resources and a supply, and the system of interest adapts to these inflows. And here's the generic reference model in layered form. It's been referred to before. And you can see at the left-hand panel, resource management, at the right-hand panel, viability management, and in the centre at the bottom, we have form, which is where all the physical systems reside, the technology, if there is any. At the top is mission management, and in the centre is behaviour and behaviour management. They all connect together. None of them operate separately from the other. They're all operating simultaneously. So it could be quite complex. Here's an example of the G.R.M. of a naval destroyer. This one's actually in combat. And you can see at the top, we've got mission management. And now it says assess situation. That was to collect information before. Identify threats and opportunities. Make decisions. Initiate action. Monitor. Behaviour hasn't changed. Down at the bottom in form you can see now we've got real equipments. At the very bottom there's an operational environment with neutrals, hostiles and terrain going into the operational environment. And we have then in the ship in form we've got radars, navigation, communications, weapons management, internal system centres, battle damage crews, weapons, ship control, weapons control, resource displays, battle damage displays, situation displays, and they're all interconnected so as to allow mission management to proceed apace. That's a more complicated version, and setting up the design of that would take some time. Problem space. It's at phases. Phase A, problem space. Explore the problem in depth. Conceive remedial solutions that would alleviate all of the problem symptoms. Next phase, phase B, concept development. Propose concepts of operations, or CONOPS, for each remedial solution. Conduct operations research, OR, into each CONOPS. Feasibility, vulnerability, effectiveness, and so on. Establish purposeful behaviour of the whole in the operational context. And then establish the viability of each conceptual remedial solution and compare, contrast, rank and select one or more of your preferred remedial solutions. And then functional design. Establish mission objectives. And strategies to achieve those objectives and strategies to overcome the threats to implementing those strategies. Transform the strategies into functions necessary to achieve the mission objectives and to overcome the threats. Establish mission and behaviour management capabilities. Whence resource and viability management. And if designed properly, that should solve the initial problem optimally and effectively. Here it is in diagrammatic form. You can see problem space, letter A in the red at the left, concept development, letter B in the centre, and functional design, letter C in the blue. System design is often regarded as difficult, complex, time-consuming and expensive. For a major integrated transport system, a fighter interceptor or a Mars rover, it can be, but where failure is unacceptable. For less challenging problems, experienced system designers may provide requirement specifications in short order, using domain knowledge, system tools and systems method, varying in days or weeks rather than years. The question then is not, can you afford to undertake system design? Then the question is, can you afford not to? System design in context. System design may be embedded in a systems methodology, which spans from problem space left to solution space right. The whole may be referred to as systems engineering, where systems methodology is the how of systems engineering. System design may extend from conceptual remedies to functional physical mapping. The output is a matched set of requirement specifications for the whole, its many interacting parts and their interconnections and interfaces. System design in context again. This time, systems engineering is shown as part of a behaviour diagram. The centre panel shows 7 process steps. The left-hand panel shows inputs to each process, including system tools and methods. The right-hand panel shows outputs from each process. Steps 1 to 6 are system design, resulting in system, subsystems and infrastructure specs. Step 7 is to create and prove the solution system. Evidently, system design forms the bulk of the systems engineering methodology, and hence of systems engineering 2. So system design is, well, it's the focus of creativity, innovation, integrity, and complexity management. In short, it is the heart and science of systems engineering. Thank you for joining me.